So in this video, we will look at how to derive an expression for effectiveness in the effectiveness NTU method. And in this particular video, we will look at how or what is the expression that we get for effectiveness for a parallel flow heat exchanger. Okay. So what we will do is we will find what is the heat transfer rate in a small elemental area across a heat exchanger. So dq can be written as u times dA TH minus TC. Okay. And we can also write this as minus m dot h CPH THO minus THI. This THO is lesser than THI. So you would be getting a negative value for the heat transfer. To compensate for that, we have introduced a minus sign here. And this dq can also be written as m dot c CPC times TCO minus TCI. And we know that this m dot h CPH, which is the product of mass flow rate and specific heat, can be written as capital CH, and m dot c CPC can be written as capital CC. And these are called as the capacitance rates. So the capacitance rate for the hot fluid and capacitance rate for the cold fluid. So the equation can be written as minus capital CH times THO minus THI, or I can write this as minus CH times DTH, that is the change in the temperature of the hot fluid, or I can also write this as CC times DTC. Okay. Further, what I can do is I can say, so now if I, so dq is minus ch times dth, and dq is also cc times dtc. So dth can be written as minus dq divided by capital CH, and dtc can be written as dq divided by capital CC. So dth minus dtc, or I can also write it as differential of th minus tc together, because it doesn't violate your mathematical rule, because d of th minus tc is going to give you dth minus dtc. Okay, both are one and the same, so I can write this as d of th minus tc, which gives me minus dq times, if you want me to write it in two steps, minus dq by ch minus dq by capital CC. So if I take minus dq as common, I would get 1 by capital CH plus 1 by capital CC. Okay, so this is the expression that we get for dTH minus dTC. And we also have another expression for dq, which says dq is u dA times, because we were talking about a small elemental area, times th minus tc. So if I substitute this dq over here, if it is substituted over here, then what I have is d of th minus tc, that is going to be equal to minus u times dA times th minus tc multiplied by 1 by capital CH plus 1 by capital CC. Okay, and so this can be, so if I bring that th minus tc to the left hand side, so that becomes d of th minus tc by th minus tc, and I would have minus u times dA multiplied by 1 by th plus 1 by capital CC. Okay, now I can differentiate on both sides over the entire heat exchanger. So if I integrate it on both sides, so I would get, so here I would get ln of TH minus TC between the entry and the exit, which we usually write it as 1 to 2. So ln of TH minus TC is what we get out of this differential. And when I differentiate dA, we are going to get A. So that is going to be minus UA times 1 by CH plus 1 by CC. Okay. And so on the left-hand side, I would get ln TH2 minus TC2, or let me put it in this way. So ln of TH2 minus TC2 divided by TH1 minus TC1, because I would be getting ln of TH2 minus TC2 minus ln of TH1 minus TC1. So ln A minus ln B is going to give me ln of A by B. So using that logarithmic rule, I have written this as ln of TH2 minus TC2 divided by TH1 minus TC1. And over here, for convenience sake, let me take CH outside. So if I do that, I would get 1 plus CH divided by CC over here. And let me take exponential on both sides. So if I take the exponential on both sides, then what I would have is, so exponential along with the logarithmic term that is going to give me simply TH2 minus TC2 divided by TH1 minus TC1. And over here, I'm going to get exponential of minus UA by capital CH multiplied by 1 plus CH by CC. Okay. And now let us make an assumption. So let us assume that CH, the capacitance rate of the hot fluid, is going to be the minimum capacitance rate. Among the hot fluid and cold fluid, either CH is going to be a C minimum or CC is going to be your C minimum. So for convenience sake, let me take CH. You can also take CC. In that case, you can take the CC outside and you would get 1 plus CC by CH. Okay. So CH is going to be a C minimum in this case. And let's say this C minimum by C maximum, let it be assumed as R, which we call as the capacitance ratio. Okay. And this term UA by CH, which is CH is what we now consider as C minimum. And this UA by C minimum is a dimensionless number, which we call as the number of transfer units. So that is called as NTU. Okay. So this expression on the right-hand side, so if you look at this R, which is the capacitance ratio, that is also a non-dimensional number. And this NTU, which is the number of transfer units, that is also a non-dimensional number. So now I have got non-dimensional numbers on the right-hand side. And if you look at the left-hand side, that is also temperature difference by temperature difference, which is again a non-dimensional number again. So this becomes exponential of minus NTU times 1 plus R. Okay. And on the left-hand side, we have got TH2 minus TC2 divided by TH1 minus TC1. So let's make a note of this particular expression. We are not complete with the derivation, but let's make a note of this guy over here. So now let's define this definition we are already aware of. Let's define effectiveness. Effectiveness is nothing but your m dot h CPH. It could be THI minus THO whole divided by the C minimum into THI minus TCI. Or it could be M dot C CPC times TCO minus TCI whole divided by. So we know that the definition of effectiveness is M dot H CPH THI minus THO divided by C minimum times THI minus TCI, or it is going to be M dot C CPC TCO minus TCI divided by THI minus TCI. You can use the subscripts 1 and 2. So this is going to be capital CH by C minimum. And here you have got TH1 minus TH2 whole divided by TH1 minus TC1. And this guy is capital CC times TC2 minus TC1 whole divided by C minimum times TH1 minus TC1. Okay. And let me get an expression for TH2 from this particular expression. So let me use this definition of effectiveness. So TH2 is going to be equal to TH1 minus epsilon times C minimum, TH1 minus TC1 divided by CH. So you're cross multiplying the C minimum TH1 minus TC1 with epsilon. So that makes it epsilon C minimum times TH1 minus TC1 divided by CH. And this TH2 is negative. So to make it positive, this becomes negative and TH1 is positive again. Okay. Similarly for TC2, that is with this expression. So TC2 is going to be TC1 plus epsilon times C minimum by CC times TC2 minus TC1. So this is what, sorry, TH1 minus TC1. Epsilon C minimum times TH1 minus TC1 divided by CC and plus TC1. Okay. Now, if you look at the expression that we had back, that is equation number 1, we said it was TH2 minus TH1 divided by, sorry, let's look at that expression a little bit. So TH2 minus TC2 divided by TH1 minus TC1. That is going to be equal to exponential of minus NTU into 1 plus R. So that is what we got. Let's check this once. Just exponential of, we don't have a minus here. So exponential of minus NTU plus 1 plus R. So now what we will do is we will substitute for TH2 and TC2 in this particular equation. So 1 by TH1 minus TC1, that will remain untouched. So in the numerator for TH2, I'm going to substitute TH1 minus epsilon times C minimum by CH into TH1 minus TC1. Then for TC2, we have a minus before, so it is minus TC1 minus epsilon times C minimum by CC times TH1 minus TC1. So that completes the left-hand side, and on the right-hand side, there is no change. So that is going to be exponential of minus NTU times 1 plus R. Okay. So now what we have is, we have already assumed the CH as C minimum. So C minimum by C minimum. So recall, we have assumed that CH is equal to C minimum, and C minimum by C maximum is going to be your R. So we already have a C minimum here. So CC becomes C maximum. So C minimum by C maximum is R. So what we have here is 1 by TH1 minus TC1. And here this TH1 and this TC1, we can combine them together and we would get TH1 minus TC1. And then what is left out is C minimum by C minimum would be 1. And we have epsilon TH1 minus TC1. And here we have C minimum by C maximum, which is R. So epsilon times R into TH1 minus TC1. Okay. And on the right-hand side, there is no change, which is exponential of minus NTU times 1 plus R. Okay. So the next thing what we do is, now you can see that effectiveness is common in the terms 2 and 3. So in the denominator, we have got 1 by TH1 minus TC1. And inside, we have already taken TH1 minus TC1. And now effectiveness and TH1 minus TC1 is common, which gives us 1 plus R, because this minus is common on both sides. And we have got exponential of minus NTU times 1 plus R. And now this TH1 minus TC1 can be taken outside, and we already have a TH1 minus TC1 in the denominator. So this is 1 minus epsilon times 1 plus R. That is going to be equal to exponential of minus NTU times 1 plus R. Okay, and so this guy and this guy can be cancelled out. And what is left out is 1 minus epsilon times 1 plus R is going to be exponential times minus NTU of 1 plus R. Okay. And so if I retain this effectiveness on one side, so effectiveness into 1 plus R is going to be 1 minus exponential of minus NTU times 1 plus R. And effectiveness is going to be equal to 1 minus exponential of minus NTU times 1 plus R whole divided by 1 plus R. So this is the final expression that we get for effectiveness of a parallel flow heat exchange. And this expression is available in your data book, so you need not memorize it, but you should learn to derive this. Okay, thank you. So next video we will talk about effectiveness, deriving effectiveness for a counterflow heat exchanger.